Tens of tons of specialized steel and reinforced composites form the chassis of machines that currently operate across the frozen expanses of Siberia and the impassable territories of the Arctic. These colossal mechanical structures possess dimensions so vast that they appear to challenge the fundamental laws of physics and traditional engineering logic. Why were these mechanical giants designed and constructed in the first place? One might assume that standard transport would suffice for northern logistics, but the extreme environment of the Russian north demands a radical departure from conventional vehicle architecture. Heavy military trucks weighing dozens of tons maneuver through deep snow and permafrost with a level of agility that suggests they are significantly lighter than their actual physical mass. It only looks obvious that a vehicle must be heavy to be strong, but in reality, the distribution of weight across multiple independent axles allows these platforms to survive where any other equipment would inevitably sink or stall. Engineers developed these specialized platforms to serve as mobile foundations for heavy weaponry and survival systems in regions where roads do not exist. One can notice how the massive low-pressure tires, often exceeding 2 meters in height, deform slightly to create a larger contact patch with the unstable ground. This technical solution ensures that the ground pressure remains lower than that of a human footprint, despite the fact that the vehicle carries a payload of 30 tons or more. The process of conquering the tundra is only gaining momentum as more specialized variants emerge from the assembly lines. Everything only gets more complicated when considering the extreme thermal fluctuations these machines must endure. The camera glides along the reinforced frames, revealing complex independent suspension systems that allow each wheel to travel nearly a meter vertically to absorb the unevenness of the frozen terrain. It is visible how the cooling systems and preheaters operate ceaselessly to prevent the fuel and lubricants from turning into solid matter at temperatures of -60 degrees. But this is just the beginning of the technical complexity required for such deployments. Because the survival of the crew depends entirely on the integrity of the vehicle, every weld and hydraulic line undergoes rigorous stress testing under simulated polar conditions. The scale of these military creations represents engineering at its most extreme, moving from the raw power of high-torque diesel engines to the precise movement of automated tire pressure regulation systems. Transition to the next level of heavy equipment involves analyzing vehicles that move beyond standard proportions into the realm of true engineering monstrosities. From the initial concept to the final deployment in the field, these machines demonstrate the absolute limit of what heavy industry can achieve when faced with the world's most hostile climates. The material remains resilient as the heavy platforms continue their steady movement across the ice. 240 horsepower and enormous torque define the mechanical heart of the Kraz 255. Why was such an extreme level of structural power necessary for a single logistics vehicle? During the most tense decades of the Cold War, the Soviet Army faced the critical problem of maintaining mobility across hostile terrain where roads were non-existent, and only a machine with the strength of a tank and the endurance of a tractor could survive. But this was just the beginning of its engineering narrative. One can notice the massive proportions of the 14.9-liter V8 diesel engine. It features 8 cylinders and a direct injection system that allows the unit to operate consistently, even when temperatures drop to extreme sub-zero levels. The deep growl of the motor can be heard from a significant distance, signaling the approach of a heavy military asset. The process of moving heavy loads is only gaining momentum through a reinforced 5-speed manual transmission. This gearbox was specifically engineered to manage the immense stress of rough ground while towing howitzers, mobile bridges, or heavy military trailers over vast distances. It seems simple at first glance, but the transmission must synchronize perfectly with a permanent 6x6 all-wheel drive system to prevent performance loss during long-range transport. The equipment gradually overcomes obstacles using a heavy-duty leaf spring suspension. This setup provides unmatched durability when traversing uneven surfaces that would shatter standard frames. One can notice how the oversized tires are manually deflated to increase the contact patch for added traction in deep mud, shifting sand, or compacted snow. Everything only gets more complicated as the terrain worsens. Tall, wide, and featuring a protruding front end, the silhouette of the machine resembles a cross between an armored hauler and a military tractor. It is visible how the structure maintains balance even when carrying light tanks or components for heavy pontoon bridges. The camera glides along the frame where engineers mounted mobile radar platforms and remote communication centers. Because the chassis was designed with such a high margin of safety, these modifications never compromised the vehicle's stability during deployment from the Arctic to dense Ukrainian forests. Many units still operate today in rural Russia and Ukraine, finding a second life in the demanding forestry and off-road transport industries. It only looks obvious that a machine built for war would retire, but in reality, its mechanical simplicity ensures it remains functional decades after its official service ended. One restored unit was even converted into a military-style food truck for a historical reenactment event. The vehicle ended up drawing more attention than the actual tanks on display, proving that its industrial presence remains formidable. The engine continues to vibrate with a low-frequency hum as the truck moves across the horizon. The material legacy of the machine remains intact, transitioning into a calm stage of civilian service. Thus ends the historical and technical overview of this key military transport asset. 38.8 liters is the massive displacement of the 12-cylinder diesel engine powering the heavy military tractor. Why did the Soviet Union require such an immense power plant during the late 1950s? The vehicle was not designed for standard logistics, but rather to carry the physical weight of the entire Soviet nuclear deterrent. This V-12 engine produced 525 horsepower, generating enough torque to pull missile platforms and tanks weighing more than 50 tons across open terrain. Development of the machine began in the late 1950s, with full production commencing by 1959. The 4-speed automatic transmission was engineered specifically to handle high-load missions over long distances without mechanical failure. One can notice how the hydraulic systems ensure smooth performance even when the environment reaches extreme thermal or physical conditions. It seems simple to move heavy equipment on a flat road, but in reality, the weight of a main battle tank requires constant, uninterrupted power. The full-time 8x8 all-wheel drive system ensures that every wheel receives torque simultaneously. But this is just the beginning. Independent suspension on all 8 axles allows the vehicle to traverse thick mud, deep snow, and loose sand. The equipment gradually overcomes cratered terrain while maintaining its center of gravity. Over 9 meters in length and weighing more than 21 tons, the vehicle possesses a physical presence that dominates its surroundings. The camera glides along the advanced cab and the tall, heavy-duty tires designed for maximum ground clearance. Its primary strategic role involved the transport of mobile ballistic missile systems, such as the R-14 and the R-17. It gets more complex further on. Large-scale engineering missions also relied on its power to move heavy construction components and tow damaged aircraft across airfields. Reliability made the tractor a staple among Soviet allies, who integrated the platform into their own domestic armed forces. It only looks obvious that such a machine would be retired, but in reality, several units remain operational in modern mining and heavy construction sectors. Following the 1986 Chernobyl disaster, modified versions of the vehicle were deployed to the exclusion zone for specialized tasks. It is visible how the rugged chassis transported lead shielding components and containers filled with radioactive waste. The machine proved so resilient that it often outperformed vehicles designed specifically for nuclear disaster response. Its independent suspension and heavy frame allowed for the movement of mobile containment systems over contaminated debris. The process is only gaining momentum as these machines continue to serve in the most demanding environments on Earth. The heavy tractor concludes its work by delivering its cargo to the final destination, where the load is transferred for the next phase of the mission. 360 horsepower. This was the combined output of the twin power units driving this specialized Soviet engineering marvel. Why would a vehicle require 2 separate 7-liter V8 gasoline engines instead of a single heavy diesel? At first glance, the dual-engine configuration seems redundant, but in reality it ensured synchronized traction and a critical reserve of power for regions where any mechanical failure meant certain death. These 8-cylinder engines worked in unison, feeding a manual transmission specifically calibrated with multiple torque-optimized gear ratios to prioritize low-speed performance over raw velocity. It does not end at this stage. 6x6 drive combined with a significantly elevated suspension architecture allowed the machine to navigate through snowdrifts exceeding 1.5 meters in depth. One can notice how the nearly 6-foot-tall tires and a buoyant frame structure enabled the chassis to partially float when traversing unstable swamps or treacherous frozen ground. The process is only gaining momentum as the vehicle moves through the most inaccessible terrains of Siberia and the Arctic. Everything only gets more complicated further on. 7 meters of length and 3 meters of height gave the machine a commanding physical presence that felt ahead of its time. The exterior featured rounded aerodynamic lines and a centrally positioned operator cab that looked as if it emerged from a classified laboratory. It is visible how the small, reinforced windows and a distinct white paint scheme emphasized its futuristic aesthetic while serving practical thermal purposes in extreme cold. The equipment gradually moved toward more ambitious goals. It was originally engineered to transport heavy equipment for the construction of remote bases, the installation of communication towers, and the support of critical scientific missions. But this is not the limit. Engineers once considered adapting this specific platform for a Soviet lunar exploration project due to its unprecedented traversal capabilities. This transition to the next level was ultimately halted because the design was deemed too complex for mass production. The machine remains a testament to a time when logistics and exploration pushed the boundaries of mechanical possibility. The massive tires eventually come to a halt as the technical journey of this engineering legend concludes. 650 horsepower was the threshold required by the Russian military in the 1990s to replace their aging Soviet-era transport platforms. Why was such a staggering amount of power necessary for a single-wheeled vehicle? It would seem that standard heavy trucks could manage logistics, but those platforms lacked the stability required for the next generation of tactical systems. This massive truck was engineered specifically to carry rocket launchers, main battle tanks, and large-scale infrastructure components with absolute reliability. One can notice the immense scale of the V12 diesel engine, which displaced 46.2 liters across its 12 cylinders. This mechanical heart generated enough torque to pull more than 70 tons of weight with ease, even when navigating steep inclines or traversing uneven surfaces. The 8-speed automatic transmission was integrated with hydraulic support systems to ensure smooth handling while operating under extreme loads. Transition to the next level. The 8x8 drivetrain worked in unison with an independent coil spring suspension system and specialized stabilizer bars. It only looks obvious that a vehicle this heavy would sink into soft ground, but in reality, the tires were linked to a central pressure control system managed directly from the interior of the cab. Visually, the machine was impossible to ignore, measuring over 11 meters in length with a high-mounted cab and an exceptionally wide frame. The camera glides along the chassis, which resembled a road-going locomotive in both stature and presence. Its deep metallic engine sound echoed across open terrain, signaling a sense of mechanical dominance and military precision. The process is only gaining momentum. This platform was frequently utilized to transport heavy rocket systems, such as the BM-30 Smerch, though it also served a vital role in moving tanks or construction materials between remote installations. Military engineers relied on its capacity when building bridges or temporary runways under intense time pressure. 4 crew members could fit inside the cab, which was equipped with dedicated navigation systems and specialized communication gear. Light armor plating provided the crew with protection against shrapnel and small arms fire, rendering the vehicle viable for deployment in various low-intensity conflict zones. It seems simple to maintain such a beast, but in reality, its longevity is the result of extreme durability and a low rate of mechanical failure. Few people realize that several units were exported to nations like Syria, Iran, and Algeria. In these regions, the vehicles underwent modifications to handle extreme desert heat and environments heavy with abrasive sand. Many of these transporters remain in active service today, continuing their work across harsh landscapes. One can notice how the heavy frames remain straight and functional after decades of use. The metal continues its service, transitioning into a calm stage of long-term operational reliability. 525 horsepower is the output generated by the massive propulsion system of the MAZ 7310. Why did the Soviet Union require such an immense increase in mobile power during the 1970s? The demand for specialized missile launching platforms grew rapidly during this decade, necessitating a machine that was significantly larger and more durable than any of its predecessors. This engineering solution resulted in a vehicle capable of transporting much heavier payloads across the most unforgiving environments on the planet. One can notice how the 12 cylinders of the 38.8-liter V12 diesel engine deliver constant torque to the drivetrain. This specific engine configuration allowed the machine to haul up to 65 tons of weight without any measurable loss in operational performance. A 4-speed automatic transmission was integrated into the design to ensure that power distribution across the heavy axles remained perfectly smooth. It only looks obvious to provide all-wheel drive, but the 8x8 system utilized here was combined with a robust suspension comprised of hydraulic shock absorbers and thick leaf springs. This combination proved ideal for traversing uneven and unpredictable terrain where standard logistics vehicles would falter. The equipment gradually adjusts tire pressure for each individual wheel to maintain traction, but this is just the beginning. This specialized control system granted the crew the ability to navigate through deep swamps, loose sand, or frozen Arctic ground by manipulating the contact patch of the tires. The physical dimensions of the vehicle were truly massive, stretching to a total length of approximately 13 meters and reaching a height of 3.3 meters. It is visible how the reinforced cabin and the extended chassis provide enough internal volume to house a crew of 4 members. Inside, the technicians operated amidst a suite of advanced systems for internal climate control, long-range communications, and satellite navigation. The process is only gaining momentum as the machine moves. The deep and continuous vibration of the V12 engine, combined with the deliberate heavy movement of the chassis, creates the impression of a rolling wall of steel. Because of this immense structural strength, the platform was frequently utilized as the primary base for mobile Scud-B missile launchers. Beyond its role as a ballistic carrier, the chassis was adapted to transport light tanks, complex radar units, and fully equipped mobile command centers. This high level of versatility ensured that it became one of the most frequently deployed assets for long-range strategic missions. Everything only gets more complicated when considering the longevity of such technology. At first glance, such a machine might seem like a relic of the past, but in reality, many units remain in active service today. They are primarily found in the most remote regions of Russia, specifically across the vast expanses of Siberia. In these locations, they continue to provide essential logistical support to advanced military outposts where no other vehicle can survive. The metal frame remains rigid under extreme thermal stress, proving the durability of the original 1970s design. The MAZ 7310 completes its deployment, sustaining its role as a heavy-duty workhorse in the harshest climates. 150% of the original tactical mobility was the benchmark set by Soviet engineers during the height of the 1980s. As Cold War tensions intensified, the Soviet Union initiated a highly strategic project aimed at the creation of a mobile missile system capable of rapid, high-precision strikes. This platform was designed to deploy both conventional and nuclear warheads with equal efficiency. Why was such a specialized vehicle necessary for this particular payload? While a static launcher provides stability, it remains a vulnerable target for aerial reconnaissance. The Oka system required a platform that was not merely durable, but nearly impossible to detect and capable of immediate repositioning after an engagement. The chassis of the vehicle carrying the OK missile was constructed with reinforced steel to withstand the immense structural stress of a launch. At its core sat a 12-cylinder V-type diesel engine generating 650 horsepower, which was mated to a sophisticated automatic transmission system. This mechanical configuration, featuring 12 cylinders within a relatively compact frame, provided the high torque and rapid acceleration necessary to transport a 7-meter-long missile across rugged landscapes. One can notice how the full-time 6x6 all-wheel drive system and independent suspension on every axle allow the machine to traverse dense forests and deep trenches. Everything only gets more complicated when maintaining launch readiness on unstable terrain, yet the vehicle remained surprisingly agile despite its lethal cargo. It only looks obvious that a missile carrier should be massive, but in reality, the Oka utilized a low, squared-off silhouette to minimize its visual and radar signature. The exterior was finished in specialized camouflage paint and featured a low-profile cap, which was ideal for concealment during quick-strike operations. Because it was smaller than the majority of strategic launchers in the Soviet arsenal, It was significantly easier to hide from the high-altitude cameras of surveillance aircraft and orbital satellites. The Oka missile itself possessed an operational range of up to 400 kilometers, providing the capability to strike high-value assets in neighboring territories within a matter of minutes. But this is just the beginning. The primary strategic advantage of the entire system was its extreme mobility. The launcher could execute a firing sequence and relocate almost immediately, effectively dodging retaliatory counterattacks or detection by enemy scouts. It was recognized as one of the most formidable mobile tactical threats present in the European theater during the final years of the Cold War era. This status remained unchanged until the system was officially retired under the terms of various arms reduction agreements signed between the United States and the Soviet Union. Transition to the next level. Few are aware that even after the official deactivation of the fleet, several units continued to function within the framework of secret military tests until the late 1990s. These remaining vehicles served as the technological foundation for the development of new generations of mobile launch systems. One can notice that while a few examples are currently preserved in military museums, the vast majority were systematically dismantled to ensure that unauthorized parties could never gain access to the technology. The legacy of the Oka thus transitions into the history of modern ballistic mobility. 1,500 horsepower is the relentless output generated by the massive V12 diesel engine at the heart of the KAMAZ 7550. This power flows through 12 highly efficient cylinders to propel a platform born from the specific requirements of modern Russian military doctrine. Why was such a radical departure from traditional heavy transporters necessary for the strategic forces? The aging fleet of legacy models lacked the modular flexibility and integrated onboard electronics required for contemporary warfare. This technological leap resulted in a massive machine engineered to provide greater cargo capacity while maintaining precise control over its strategic payload. The process is only gaining momentum. One can notice how the automatic 8-speed transmission operates in tandem with an intelligent electronic management system. It does not merely shift gears, but actively optimizes torque distribution to ensure that fuel consumption remains efficient even during long-distance missions under a full load. This electronic brain serves as the intermediary between the raw power of the V12 engine and the complex demands of the 16x16 drivetrain. It only looks obvious to power all 16 wheels, but in reality, maintaining traction for a vehicle of this scale requires constant mechanical synchronization. The equipment gradually adapts to the surface using a hydropneumatic suspension system equipped with sophisticated electronic control. Even when traversing uneven terrain or crossing broken ground, the system performs automatic leveling adjustments across the entire length of the launch platform. One can notice the chassis remains perfectly horizontal, a critical requirement for the stability of the sensitive equipment mounted above. Everything only gets more complicated when considering the sheer physical dimensions of this rolling missile base. 20 meters of length and nearly 4 meters of height define its presence on the landscape, yet the machine is designed to move with surprising quietness. The modular architecture allows the platform to be reconfigured with interchangeable components, ranging from additional armored plating and surveillance arrays to specialized strategic missile launchers. Within the reinforced cab, the environment is strictly regulated by climate control systems while light armor protects the crew during transit. Automated navigation systems and onboard sensors work alongside global positioning technology to ensure the vehicle reaches its destination with absolute precision. The transformation does not end at this stage. This platform serves as the primary transport and deployment vehicle for the RS-24 Yars, which stands as one of the most advanced intercontinental missiles in the current inventory. Transition to the next level. Because the project continues to evolve, engineers are constantly refining the integration of sensors and launch hardware to maintain strategic readiness. The deployment of these units marks a gradual phase-out of older generation transporters as the military shifts toward this standardized component of strategic operations. The massive machine settles into its final position as the hydraulic systems lock, ready for its next command within the broader defense network. 710 horsepower. This is the mechanical force generated by the V12 diesel engine driving the Vityaz DT-30PM through the most hostile environments on Earth. Why was such an immense power plant necessary for a single transport unit? It would seem that standard heavy trucks could navigate frozen plains, but in the extreme conditions of the Arctic, wheeled vehicles inevitably lose traction and sink into the permafrost. This militarized super tractor was specifically engineered as an articulated tracked vehicle to overcome geographical challenges that stop all other machinery in their tracks. The power is distributed evenly between two massive articulated modules that define the vehicle's unique silhouette. The front section houses the control cab and the primary propulsion systems, while the rear unit is dedicated to transporting heavy cargo. Everything only gets more complicated as the terrain shifts. One can notice how the automatic transmission, equipped with multiple gear ranges, adjusts the torque to adapt traction across varying surfaces without losing momentum. Instead of traditional tires, the machine moves on continuous tracks that provide constant contact with snow, ice, deep mud, and soft sand. The suspension system is reinforced with heavy-duty torsion bars and hydraulic elements. It is visible how the equipment gradually adjusts to maintain a firm grip even when traversing extremely uneven or broken terrain. But this is just the beginning of its structural complexity. Measuring approximately 16 meters in length, the vehicle resembles an articulated train as it maneuvers. The flexible coupling between the two modules allows for a high degree of mobility, preventing the chassis from snapping under the stress of jagged ice or rocky ridges. At first glance, the design appears purely functional, but in reality, the futuristic cab with its reinforced body and small windows is built to withstand extreme pressure and impacts. The white or camel coloring of the exterior allows the massive structure to blend into the desolate Arctic landscape during operations. Russian military forces deploy these units for critical missions throughout the Arctic Circle, where they serve as the primary lifeline for remote outposts. The rear module carries loads weighing up to 30 tons, including sophisticated electronics, heavy weaponry, and essential supplies for research stations. Transition to the next level. The vehicle is also utilized for the specialized task of installing communication towers in regions that are considered nearly inaccessible by any other means of transport. One can notice the stability of the platform even when it is positioned over frozen lakes or entirely unspoiled natural areas. What makes the machine truly unique is its ability to remain fully operational in temperatures dropping below -50 degrees Celsius. The metallurgy and fluids are designed to resist freezing, ensuring the mechanical components do not become brittle in the polar cold. The molten stream of logistics continues to flow as the vehicle concludes its passage through the ice, ready for the next phase of its mission. 28 meters of length and over 4 meters of height characterize the physical presence of the MAS 7907. Why was such a colossal machine conceived in the 1980s for the Soviet military? It would seem a standard heavy truck could handle logistics, but the specific requirement was the mobile and secure transport of massive intercontinental ballistic missiles. The project remained strictly classified for decades, and only recently has its engineering complexity gained public attention. The propulsion system of this transport giant was far from conventional for its era. A gas turbine producing 1,250 horsepower served as the primary heart of the machine. But this is just the beginning. One can notice how the turbine does not drive a traditional gearbox, but instead pairs with individual electric motors mounted directly onto each of the wheels. 24 wheels distributed across 12 separate axles provided the necessary surface area to support the immense weight. Every single wheel possessed its own independent power source, representing an evolutionary concept for the period. The suspension was fully electronic and active, featuring a system for automatic load leveling that managed weight distribution with millimeter-level precision to ensure absolute stability. Even when the vehicle was carrying a load exceeding 150 tons, the internal computers could adjust the height and tilt in real time. Transition to the next level. The physical silhouette of the machine looked nothing like a traditional truck. It featured a long, narrow cabin and a body that stretched across the terrain like a land-bound freight train. It is visible how the dark paint and specialized chassis were designed for deep cover operations. Unlike most military vehicles that rely on loud diesel engines, the combination of its turbine and electric motors produced a strange, distinct metallic hum. It seems simple to assume such a machine was a mere experiment, but in reality, it was tested extensively at secret military bases where its performance impressed high-ranking officials. The vehicle was designed to transport intercontinental nuclear warheads far from the surveillance paths of Western satellites. Although the MS 7907 never entered mass production, many engineers still consider it the most complex and ambitious land-based military vehicle ever constructed. A single prototype remains today, under constant watch within a secure military facility. The massive structure stands as a testament to the engineering limits of the 20th century. The history of this machine concludes this phase, remaining a singular example of extreme heavy transport development. Tens of tons of specialized equipment and reinforced armor plate represent more than mere transportation. Why were these platforms engineered to survive conditions that would destroy conventional machinery? At first glance, they appear as simple, heavy-duty trucks, but in reality, they are sophisticated technical responses to environments defined by thick mud, sub-zero ice, and even high levels of radiation. These vehicles function as mobile laboratories for extreme durability, operating on a level of brute force that few other engineering traditions have ever attempted to reach. The equipment gradually reveals its purpose through its presence in nuclear testing zones and high-stakes secret missions. It is visible how the heavy chassis supports weights that would crush standard axles, including the massive structural loads of strategic ballistic weapons. This is just the beginning. Historical evolution has dictated that these machines must carry more than just weight. They serve as a physical record of decades of technical ambition and strategic innovation. One can notice how the design philosophy prioritizes mechanical redundancy over aesthetic form. The camera glides along the reinforced frames that have traversed thousands of kilometers during extreme explorations and intense territorial conflicts. Everything only gets more complicated as the legacy of these giants moves forward into the current era. The engineering solutions developed for these platforms remain a fundamental component of the technological history of heavy transport. Each unit transitions from the design phase to the field, where it fulfills its role as a critical asset in the most demanding geographical zones on the planet. Thus ends the overview of the specific engineering milestones and the powerful machines that have shaped the development of extreme heavy-duty transport. The technical record of these mobile giants concludes this phase of the study, leaving their specialized mechanisms ready for the next decade of operation.